Hello, my name is Sabrina Fowler, and today I'm going to talk to you about Gröbner bases. Gröbner bases are a key ingredient in a lot of computations in commutative algebra. So today I'm going to tell you what they are, how we can compute them, and what sorts of problems we can use them to solve. Note that the setting for this talk is going to be a standard graded polynomial ring in finitely many variables over a field. And I want to begin by talking about a couple of motivating questions that we can use Gröbner bases to solve. So the first of these is the ideal membership problem, which asks, given an ideal, given a ring element, is my ring element in my ideal? And this is a problem that if the answer is yes, we can sometimes solve by just staring at the generators, staring at the ring element, and finding the coefficients we need. But if the answer is no, it's a lot harder to answer for sure. However, this problem is completely solved by Gröbner bases. You can ask Macaulay 2 this problem, and Macaulay 2 will compute a Gröbner basis to give you your answer. The next problem I want to talk about, I'm calling the implicitization problem. And this problem asks, if I have a set of points in affine n space that are given by some polynomial functions of a parameter t, can I find all polynomials that vanish on these points? And this really boils down to asking, can I find the kernel of this map that sends a variable to its corresponding function of t? And this is another problem that we can partially solve by staring. We can stare at the functions that define these points and we can say, aha, I found a polynomial that vanishes. But it is hard to know when we have found sufficiently many of those to actually generate that entire kernel. So we're going to be able to use Gröbner bases to make sure that we've found the entire kernel here. And the solution that we're going to talk about can easily be extended to the case where you have more than one parameter defining your points as well. So I hope that you find these problems exciting and compelling, because we're going to take a little detour and build up to this definition of Gröbner basis so that we can work with it to solve these problems. So the first definition I have is a monomial ordering. And this is going to be a total ordering on monomials. And when I say monomials, I'm going to mean monic. So I don't care about their coefficient. I'm just looking at the variables. And a total ordering means that if you hand me any two monomials, I can always tell you which one is larger. And I need my total ordering to satisfy two properties. The first is that 1 is the smallest monomial, and the second is that I need my ordering to be preserved under multiplication. So if I have monomial 1 larger than monomial 2, and I multiply both of them by monomial 3, I need the product that has monomial 1 in it to still be larger. So these two properties are all we need to satisfy to have a monomial ordering. But if we satisfy this third property, then we call our monomial ordering degree-wise. And this property says that my monomial ordering respects the standard grading. So if you hand me two monomials of different degree, the one with the larger degree is going to be larger under my ordering every time. And this is what it means for a monomial ordering to be degree-wise. So let's talk about a couple of examples of these orderings. And before we get into the rules that define the ordering, we need to first order the variables, because we're going to be talking about comparing these tuples of the powers. And so we need to agree on what order we put the powers into this tuple to compare them so that they're comparable. And the first ordering that I want to talk about is called the lexicographic order, abbreviated lex. And so we have this condition about the first non-zero entry of the difference of the tuples being positive. And what this means is you hand me two monomials and I find the largest variable under this variable ordering that appears anywhere in either monomial. Whichever monomial has more of that variable, that's the larger one. So if I look at this largest variable and it doesn't appear anywhere, I go to the next largest. If I look at this next largest and they both have the same amount of that one, I go to the next one, and I go until I find where one monomial has more of that largest variable. This ordering is not degree-wise, but sometimes we are interested in having something degree-wise, and so we look at the graded lex order, which is degree-wise. And it says, give me two monomials. If they're different degrees, we have our answer. The one with larger degree is larger. If they have the same degree, then we use the lex order to decide which one's bigger. So to illustrate the difference between these two orderings, let's look at the two variable case where x is larger than y. And in this case, if I'm using the lex order, the monomial x is larger than the monomial y squared because the largest variable that appears in either one is x, and the monomial x has more of those. But if I look at the graded lex order, then y squared is bigger because it has larger degree. So that's what a monomial ordering is. Those are the two examples of these orderings that I'm going to use during this talk. For the next couple of definitions, we're going to have a fixed monomial ordering. So pick your favorite. Could be one of the ones I just told you about, could be a different one. There's lots. But once you have a monomial ordering in hand, grab a polynomial, and it is going to have a leading term and an initial term. So we're going to look at this unique way that I can write f as a k-linear sum of monomials. I'm going to find the term with a non-zero coefficient that has the largest monomial. That term is the leading term, coefficient and all. The monomial that I picked that was the largest one is the initial term. So for example, we can look at this polynomial f in the three variable case, and the monomial ordering we have is lex, and we're going to say that x is greater than y is greater than z. So I'm going to look at each of these terms and look for the one with the most x's in it. And that's this one. And that's all x cares about, is which one has the most x's. So my leading term is going to be that 2x cubed, the entire term. And then the initial term is just the monomial x cubed. So this is the terminology that I'm going to be using in this talk for leading term and initial term. This is by no means standard in the literature. So if you are reading about Gröbner bases, make sure that you know what they mean when they say these words and what words they use to mean these things, because sometimes people say leading term to mean what I'm saying is the initial term and all kinds of stuff. So in this case, leading term includes the coefficient, initial term, just the variables. Okay, so that definition, we had a fixed monomial ordering and some polynomial. Now we're going to fix a monomial ordering and think about an ideal. This ideal has an initial ideal. And this is the ideal that is generated by the initial terms of all of the elements of I. And so you may say to yourself, well, can I just take a generating set for I and then take the initial terms of those generators? Will that generate this initial ideal? So let's look at an example to investigate this. So we have this ideal I generated by these two polynomials, and we're going to fix the ordering to be the graded Lex order, x greater than y greater than z. So first, let's consider this ideal J that's generated by the initial term of the first generator and the initial term of the second generator. What are those? Well, the first generator, both terms have the same degree. So I look for the one that has the most x's in it, and that is xz. And then I'm going to look at the second generator, which is not homogeneous. So all I have to do is look at the degrees and say x cubed has larger degree. That is my initial term there. Okay, we're considering this guy. Now let's consider f. And I'm going to take f to be x squared times this first generator, and then minus z times the second generator. So what do I get here? I get x cubed z minus x squared y squared minus x cubed z plus z cubed. And we have x cubed z minus x cubed z cancel, and we're left with z cubed minus x squared y squared. So this is f. I obtained f by taking an R linear combination of the generators of I. So this f is definitely in I. So what is its initial term? The initial term of f, let's see, is just the one with larger degree. So it's going to come from this term, minus x squared y squared. But for the initial term, I don't care about this minus 1 coefficient. So the initial term is just x squared y squared. And that is the initial term of an element in I. So this should definitely be an element of the initial ideal of I. It's a generator even. Now I'm going to claim that this ideal membership problem is x squared y squared in J can indeed be solved by staring. If I look at these generators for J and I look at this term, there's no way that it's in there. So it turns out we cannot take any old generating set for I, take its initial terms, and generate the initial ideal, because I just found that J is indeed not equal to the initial ideal of I. I found an element that is in one but not the other. So that leads us to our titular Gröbner basis. A Gröbner basis for an ideal is a generating set for I that does what we hope that it would do. Its initial terms do indeed generate the initial ideal of I. So now that we know what a Gröbner basis is, we're going to be able to use it to solve this ideal membership problem. And in order to do that, we're going to need this theorem called the division algorithm. And this division algorithm is interesting because we are going to be able to divide by a set of polynomials all at once. So the ingredients here are, we're going to take a ring element, we're going to take a set of ring elements, and we're going to fix our favorite monomial ordering. Given those three things, we can always write f as a sum of an R linear sum of elements of my set G plus some remainder R. that are going to satisfy a couple of properties. The first is that the initial term of f is going to be greater than or equal to the largest initial term that comes from this sum part. And then we're also going to have our remainder satisfying this rule that none of the initial terms of any of these elements of G are going to divide this remainder R. And the exciting part is if we do this division algorithm using a set G that is a Gröbner basis, then this R is going to end up being unique. And we are going to use this notation to mean the remainder on division of f by G. And this is the exciting part. This is what's going to allow us to solve this ideal membership problem. So I'm going to go ahead and prove this exciting part to you. So we are going to start with two different ways of writing f satisfying this division algorithm. And what we're able to do, since we have that these are both f, so they're equal, I can take this r prime and subtract it to this side, and then take this sum and subtract it over to this side, and I'm able to write r minus r prime is equal to the sum from 1 to s of vi minus ui times gi. When I have the sums on the same side of the equal sign, I can combine them together. And this is clearly an element of this ideal generated by the GIs. Now, since G is a Gröbner basis, the initial terms of the GIs generate the initial ideal of this. And this element is in here. So the initial term of r minus r prime is in the ideal generated by the initial terms of the GIs. Now, if we think about how subtracting polynomials works, the initial term of r minus r prime is a term that appears in either r or r prime. I guess it could be both. It could be that they both had it, but different coefficients and it didn't cancel. But either way, it's in one or both of r or r prime. And our division algorithm says that the initial term of these GIs doesn't divide any monomial that appears in R, no matter how you write it. It's not going to appear in a monomial here or a monomial here. So we have that the initial term of GI does not divide this term for any I. Okay, so I have this element in this ideal generated by these things, but none of these things divide this element. And these are all monomials, right? This is a key fact here, is that I have a monomial in a monomial ideal where none of these monomial generators divide this element. The only way that this is possible is if r minus r prime is 0. That's the only element of this monomial ideal that doesn't divide any of the generators. And, oh, not in 0, is 0. So this means r minus r prime is 0 if its initial term is 0, meaning r was equal to r prime all along. Now notice I'm not making any claims about the ui's and the vi's being unique. It is possible to write f in two different ways, satisfying the division algorithm when we're dividing by a Gröbner basis where these coefficients are different, but the remainder is always going to be the same. This leads us into a corollary, the ideal membership criterion, which says, let's take a Gröbner basis, let's take a ring element. Well, my ring element is going to be in this ideal if and only if, when I take my ring element and I divide by all the elements in the Gröbner basis using this division algorithm, the remainder I get is 0. And we can see this by looking at this way that we can write f given this theorem. So the forwards direction, suppose f is in I, well, then I can write f as an R linear sum of the generators of I. I don't need any remainder. This is going to be 0. Other way around, suppose that this remainder is 0, then, oh, look, f is an R linear sum of the generators of I, so f is in I. So this is really exciting. Now we have this problem solved. Let's do an example. So let's look at this ideal I, generated by these two polynomials that I'm calling f and g. For now, I am going to boldly claim that this is a Gröbner basis with this Lex ordering and this ordering on the variables. For now, take me on faith that that's true. And let's consider this polynomial h. And we want to know, is h an element of I or not? So let's use this ideal membership criterion. Let's do the division algorithm. So I'm going to take my polynomial h and divide by f and g. So when we are using this version of the division algorithm, we need to know what the leading terms are of all of our players here. So if I look at f, we're using the Lex order, so I don't care about degree. I just care which term has more y's in it, and that is this first term. And then if I look at g, which term has more y's? Neither of them have any y's, so I move on to z. Which term has more z's? This one. And then I look at h, and its leading term is going to be this one with the y in it. So the way that this division algorithm works is I have to use leading terms of the guys I'm dividing by to cancel the leading term of the thing I'm dividing. So if I look at f and I look at g, I could multiply by zx and use f to cancel, or I could multiply by yx and use g to cancel this term. This is what I meant by saying that the coefficients aren't the same, right? But we are going to get the same remainder no matter which path I choose because we are dividing by a Gröbner basis. And our lives are going to be easier in general if we use the higher or the larger initial term to do our division. So I'm going to use f. So what I'm going to do is I'm going to write f here. And what did I say I need to multiply by? Zx. So I'm just going to multiply the whole thing by zx and subtract to cancel off that leading term of h. So my yzx cancels, and then I have minus 2zx cubed, but then I'm adding a zx cubed, so I'm left with just minus 1 zx cubed, and then I also have that z squared. So what this tells me is that as I'm writing h in that way that I'm able to via the division algorithm, that first coefficient is zx and it is on f. Okay, so now I need to identify the leading term of this intermediate guy here. And I don't care about degree, I just care who has more z's, and that is z squared. And then I have to use g to cancel this. So I'm going to put g here, and I need to multiply just by one more z to get that to cancel. So now I have z squared minus z squared, and zx cubed, or excuse me, minus zx cubed plus zx cubed. I actually end up with 0. So I'm going to put, what did I do? A z times g, and then plus 0. So this tells me I divided by a Gröbner basis of I, and I got a remainder of 0. Therefore, h must be an I by this ideal membership criterion. So hopefully now you're thinking, oh yeah, this Gröbner basis thing seems cool and helpful. How can I get me one of those? Well, you're in luck because my next section is called Constructing Gröbner Bases. And in order to do this, I need one more definition. And we're going to define an S polynomial. So if I fix my favorite monomial ordering, which you'll notice is a theme in a lot of these definitions, they depend on which monomial ordering you choose. Fix a monomial ordering, take a pair of polynomials, I can compute their S polynomial. And the first thing I need to compute this polynomial is I need to look at the least common multiple of their initial terms, and then I can compute this S of f and g. So I'm going to take f, and I'm going to multiply by this least common multiple and divide by the leading term of f. And because the leading term of f is just the initial term of f with a coefficient, and we're working over a field, so it's okay to have a coefficient that we're dividing by, I can really think of this as being, I've got the initial term of f down here, which divides m, so I'm good. This, what looks like a rational function is actually going to be a polynomial. It's always going to cancel every time. And then that similarly happens over here in front of g. And this is going to be a useful tool in finding a Gröbner basis. So the next thing we're going to talk about is Buchberger's criterion, which is a way to check if you have a Gröbner basis or not. And this says, take an ideal, and if you want to decide if you have a Gröbner basis or not, well, it only happens if and only if you take every pair of polynomials in this set, and you first compute their S polynomial, and then you take that S polynomial and you divide by all of g using the division algorithm. If you get a remainder of 0 for every single pair, then you have a Gröbner basis, if and only if this happens. Okay, so now we have a way to test if we have a Gröbner basis or not. Let's test and see if I was telling the truth earlier when I told you we had a Gröbner basis. So we had this ideal I, and remember we decided that this one was called F and this one was called G, and that these were my initial terms. So let's see if we actually have a Gröbner basis here or not. So the first thing we need to do is compute the S polynomial of f and g. So the least common multiple of the initial terms here is just the multiple because they don't have any common factors. So I'm going to take yz and then divide by y, the initial or the leading term of f. In this case, the leading term and the initial term are the same because they're monic. I'm going to multiply that by f and then subtract, put yz up here again, but this time divide by z, multiply by g, and then let's see what I get. So as promised, we have nice canceling happening, so we don't have any rational functions. We've got z times f minus y times g. And let's see, we've got zy minus zx squared minus yz. Oh, I guess I should have written the other one, yz2. Oh well. Plus yx cubed. And we're commutative here, so this order doesn't really matter. Those cancel as intended. The whole point of this S polynomial is that the terms that came from the leading terms of f and g are going to cancel with each other. So now we are left with yx cubed minus zx squared. So now that I have this S polynomial, I need to divide by my set and see what remainder I get. So let's see, what is the leading term of this? It's the one with the y in it. Okay, so the important thing to note here is the way that I make this division algorithm work. The actual algorithm says I have to use these initial terms to cancel this guy. In theory, I could use this x cubed and I could multiply this guy by y and then cancel this term that way. But that is going to cause the restriction on the coefficients, the ui's. That won't be true anymore. That fact about how the initial term of f is greater than or equal to the yada yada, right? So the rule is I have to use these guys to cancel this guy, and which means I only have one choice because only one of them divides it. So I have to use f. So put f there, and I need to multiply by x cubed to make this work. And now I'm left with x to the 5th minus zx squared. Leading term here is this minus zx squared. And now I have to use g. And let's see, there's g. I have to use, I have to multiply by x squared. And then that still won't work. I have to multiply also by -1. And now I have minus zx squared plus zx squared. And I have x to the 5th minus x to the 5th. So I do end up with 0. I did not in fact lie to you. This is in fact a Gröbner basis, as proved by Buchberger's criterion. So, okay, now we know how to check if I have a Gröbner basis or not, but how can I make one? And that happens via Buchberger's algorithm. Okay, so step 0. Let's start with a generating set for some ideal I. And the first thing we're going to do is we're going to check and see, is this a Gröbner basis already? Because that would be cool if so, right? We're going to compute all of these S polynomials and do the division, see what remainder we get. That's what this notation means, right? And then if we get any non-zero results, that means, we did not have a Gröbner basis. Buchberger's criterion has failed. That was an if and only if. So if I got non-zeros, no way that was a Gröbner basis. Well, let's take those non-zero remainders that I got and throw them back into G. Just make G a little bit bigger. Is it a Gröbner basis now? Well, let's check. So we're going to then go back, compute all these things again for my new G that I've made, and see if I get any non-zero remainders that time. And we're just going to keep computing and adding and computing and adding until suddenly Buchberger's criterion will be satisfied and we will have a Gröbner basis. And this algorithm is guaranteed to terminate. And that is because we are working over a nice handy-dandy Noetherian ring, and we're creating for ourselves a ascending chain of ideals. So it's going to have to stabilize. Okay, now we know how to make a Gröbner basis. Let's make one and solve a problem with it. So the last section, we're going to talk about how to solve the implicitization problem. And we're going to need one more theorem to make that happen. And it's called elimination. And for this theorem, we're going to take an ideal, and instead of fixing your favorite monomial ordering, you're going to pick my favorite. We have to pick this ordering of Lex where the variables are ordered in this way, where the ones of higher index are smaller. And we're going to consider this inclusion of, we have our ring R here, and we have this other ring where we just adjoin the smaller variables. And we're considering the inclusion, but we're really thinking about going backwards via this inclusion. So the first part of this theorem says, if I have an ideal, I, that lives upstairs in R, I take its initial ideal and I send that back through this map. Look at just the elements that have the smaller variables in them. Take out all the elements with the big variables. That's the same thing as first, starting with I here, sending that back through and taking the initial ideal downstairs. And that's true for all I. So I can throw out as many of the bigger variables as I want. I can do this in either order. I can start, take the initial ideal on this side, and then go backwards. Or I can go backwards first, take the initial ideal of what I get, and they are equal. So a consequence of this is if I have a Gröbner basis for an ideal I upstairs, then if I take that Gröbner basis and I look at it, send it back through downstairs, that is still a Gröbner basis for I downstairs. So what this means is if I have a Gröbner basis for I and I throw out all of the elements that have these large variables in them, that is going to be a Gröbner basis for I, where I threw out all the guys who had the big variables in them. So this is the last ingredient that we need in order to answer this implicitization problem. So what we want to do is find the defining ideal of these points in affine 3 space. And as we discussed earlier, what this means is we want to find the kernel of this map where I start in K adjoin 3 variables and I land in K adjoin T, and I send each variable to its corresponding function of T. And you might be saying, why did you write it like that? Well, because we're going to use elimination by taking a detour here. So if we take a detour, oops, I don't know why I keep doing that, through this ring, and we have this map pi do what I've already written, what we expect it to do, and we think of this as this inclusion that we were talking about in the elimination theorem, then what we are interested in finding right now is the kernel of this composition, the kernel of pi after I. And what that means is if I look at the kernel of pi in this middle step, if I find a Gröbner basis of it, and I use this particular ordering that they told me to use, then I can send it backwards, and I will find a Gröbner basis of this ideal that I'm looking for. And a Gröbner basis is in particular a basis, it's a generating set, so I will know that I have found the entire kernel, which was the crux of this problem, is how do I know that I have an actual generating set of this kernel instead of just some elements. So the game plan is we are going to use Lex and put the variables in this particular order, like the theorem told us to, and using this as our ordering in hand, we will use Buchberger's algorithm to compute a Gröbner basis of this ideal here in the middle, and then once we have that Gröbner basis, send it back. And it is well known that the kernel of this type of map looks like this. So we have an ideal in hand, we have an ordering in hand, and we can compute a Gröbner basis, and then we can just throw out all of the elements that have t's in them, and we will have a Gröbner basis for this ideal that we're actually interested in. So I went through the liberty of doing these computations. So first step, we take our generating set, right? Step 0 was get that generating set. Now we are going to do a few loops where we start with these guys. We identify who their leading terms are, and we need to compute these S polynomials. So the S polynomial of the first two is this. We go to do the division, and none of these leading terms divide this leading term, so I can't do much, and it's its own remainder. Looking at the next pair, we get this, and this one, the leading term here, or excuse me, it does have someone up here who divides it, so we can do one step of the division, but then we're still left with a non-zero remainder. And then this last pair gives us an S polynomial who is, again, its own remainder. So we have 3 unique non-zero remainders. So let's take them and throw them into G and see, do we have a Gröbner basis now? And so we throw those 3 in. Now we have these 6. And we're already guaranteed to have the remainder when we divide these 3 by G be 0, because we know that we get these things that are now in G. So we just have to check the new pairs. So we have to check G4 with each of these 3, and then G5 with each of these 3, and then G6 with each of these 3. And what ends up happening here is we get this non-zero remainder appearing twice from a couple of pairs. This one appears once, this one appears once, and the rest are all 0. So we end up with 3 more non-zero remainders. So we throw them into G and try again. So in this loop, what ends up happening here is we get this non-zero remainder popping up 4 different times, and the rest of them are all 0. Okay, one more to throw in. Now we have 9, and we only have 8 things to check, right? Because we already know G1 through G8 are going to be good. But we have to compute the S polynomial and then do the remainder on division for G9 paired with the other 8. And it turns out for the first 7, it's going great. We get 0. Happy times. And then the last pair that we have to check, G8 and G9, we compute the S polynomial, we divide by G, and our remainder is non-zero. So we have to go again. Now we have 10 things. However, we're done. This ends up being sufficient. We have 9 things to check this time. They are all 0, and we're good to go. Okay, so back to now that we have this thing, what are we doing with it again? This G is a Gröbner basis for the kernel of pi. So we can take it, send it back, and we'll get a Gröbner basis for the kernel of pi after I. So what do we need to do to send it back? We just need to look at only the elements that don't have any t's in them. So let's see. We don't need G1, G2, G3, or G4. There's a T, there's a T. That should be it. These 4 that are left should do it. And indeed, now we have a Gröbner basis of kernel of pi I. So we have a Gröbner basis, which is a generating set, so we know that we found sufficiently many polynomials that actually are going to generate all of the ones that vanish on the points we were looking for. So thank you so much for listening. I hope you are excited about Gröbner bases now.